Thank you for the introduction. So I'll talk about a policy language and an enforcement mechanism for microservice-related safety properties. To understand the microservice design paradigm, let's consider the example of a hospital management application where a user can request for some medical test from an external lab. And in this case, the application is going to be comprised of loosely coupled components, which we call as services. So in this case, we have front-end, de-identify, and lab. These services can implement their functionality by using the other services API endpoints. Like here, the front end is calling de-identify followed by the lab endpoint. Now, when a request arrives at, say, front end, or for that matter, just any other service in this application, its execution will involve a tree of API endpoints. And I refer to this execution trace of just a single request as the service tree. Structurally, it's simple. The nodes are going to be your API endpoints, and the edges will be your will denote that your parent is sending an HTTP message to the child. So in the context of our previous example, we will have front end first sending a request to de-identify, and then de-identify will have its own tree. Upon receiving a response from the first branch, will the control go into the second branch, and so on. Now, this tree actually depends upon a lot of factors and can vary across the runs. Also, the implementation of services is handled by independent teams with little to no coordination between each other. This makes it difficult and as well as at the same time important to reason about the global behavior of your application. And that brings me to the goal of this work. How do you specify and enforce the correct behavior of a microservice application? While requiring that your application treats services as black boxes, meaning we don't have access to their code, and the enforcement mechanism is non-invasive, meaning you're not required or supposed to be updating the service code to bake this enforcement mechanism into your application. Now, one might ask why these requirements? Well, it is motivated by the fact that this will help us decouple the enforcement mechanism or the policy and the application implementation. Again, why is it useful? Because in reality, these microservice applications have different teams and they have different kind of policy requirements. For instance, you might have your data compliance team wanting to enforce some GDPR or HIPAA-like compliance requirements versus your development team wanting to have some implementation-specific policies. And likewise, your testing team might want to have some conditions on which versions to use along which paths. Now, what makes it challenging? Well, as we noticed, the execution trace in microservices will be trees, which means your properties will also be conditions on this tree structure. And the existing mechanisms are unable to work with tree structures, and all they can specify and enforce are these very coarse-grained and simple policies, which I refer to as pairwise policies. To understand what it might look like, well, consider this front-end application could have written to a database or could not have been allowed to. But you will not be able to express interesting properties which actually depend upon the intermediate interaction between your front end and the database. Like you want your database to be disallowed only if in the intermediate services you've touched upon a data belonging to the European region. Now, what was it that helped us actually come with a workaround for this challenge? Well, it is this key insight that your service trees can be viewed as nested words. This idea of nested words has been around for roughly 2 decades now. The idea is simple. You have your tree, you can consider the traversal, the pre-order traversal of this tree as just capturing the linear structure of your tree, and we'll do so as a sequence of call and return symbols. Something like you're traversing it and lining up all these API calls. The next part is to represent the hierarchical nature of your tree, meaning captures some notion of parent-child relationship. So we're able to do that if we connect or come up with a relation between your call symbols, a call to the front end, and its corresponding return. Notice that everything nested between these two symbols will be either the children or the descendants of your front end. Now, with this key insight as our center, we first design a policy language which can talk about what are your allowed set of trees, and then an automata-based distributed runtime monitor. And particularly, we use visibly pushdown automata. So in the rest of the talk, we'll first look at the policy language. I'll follow that up with the enforcement mechanism, and finally, the non-invasive implementation. Well, let's consider an example de-identification policy where your compliance team wants that you don't want to leak your personal health information to a third party. So what you want here is that front end should call de-identify only, should first call de-identify in one of its child, and then follow it up with other child, which can be lab. In SafeTree, you will have express this policy as follows. The idea is simple. You'll first start by describing what the root of your tree should be, where you should start matching the property you care for. And here I'm just saying that a tree with just any endpoint should be matched for the policy on the right. Now, what's the policy talking about? It is first specifying that the root of your tree should be front end. And then we talk about the interesting bit trying to describe that the first subtree, that there should exist at least two children. One of them should be a subtree satisfying the property P1, which says that it should have the root as de-identify. This will be followed by checking for the existence of another subtree rooted at lab. Now, our paper talks about other expressive language constructs to talk about more hierarchical policies like conditions over all your subtrees or conditions over all your paths. And also we support a way to just specify a regular expression and match your pre-order traversal or the linear structure of your execution. So now that we've looked at an example policy, how do we enforce that policy? The key point over here again stems from our insight that if you have a policy, you will view that as a set of acceptable service trees, which we'll mathematically model as a set of nested words. Now, the nested word literature has shown that there's this special kind of pushdown automata called visibly pushdown automata, which can accept certain set of well-matched nested words. And so what we do here is we have a policy, we compile it into a visibly pushdown automata. And now one might wonder, do you have any formal guarantees that you offer for this compilation procedure? And we indeed prove the soundness theorem, which says that the nested word interpretation for our policy language, which we have defined, is equivalent to the language of the compiled VPA. What this means is, if you take a word that your policy says should be accepted, and if you run the VPA on that word, the VPA should go to an accepting state. And similarly, if you go in the reverse direction, you start with the VPA, run it, it's accepted, then the policy should also be saying that it is an acceptable word. Now that we've realized that our recognizing mechanism is going to be this compiled VPA, how do we implement a monitor which will non-invasively keep on looking for any violations? Well, the monitoring setup is your service, all your services running in independent containers. And the VPA that we just compiled can be approximated to just be a transition system. You start with a given state or a configuration, here represented as S, and then you see an API endpoint, which is our symbol, and transition to another state T. Operationally, this VPA is going to read HTTP messages flowing around in your application. And the HTTP message will have identifiers in its header fields, which will carry the configuration header, configuration of your VPA. And also, you can check the header and know what symbol you are reading. And then the VPA will update the state. Now, we go for a distributed design of this monitor. Why? Because a centralized scenario where you just had one VPA serving all the requests floating around in your application is not scalable. The idea is simple. You're trying to move the transitions closer to the services. What that looks like is your service containers are now going to be having co-located local monitors. Essentially, it's just the deconstructed version of your VPA. Let's say you're looking at the pink service. Lab is going to only have local monitor, which represents or encapsulates transitions on that symbol. And then the VPA configurations we were carrying in our header acts as the medium through which we coordinate between these local monitors. And we non-invasively implement using service meshes, which is a new networking layer. All that does is you have independent containers running these monitors outside your application. Finally, just to highlight some of the results, I will point out that our latency overhead and the memory overhead is quite minimal. The way we evaluate them is by taking benchmark microservice applications, running them on 9 case studies across varying number of nesting. And we noticed that when you measure the latency overhead of running this monitor, in the worst case, you've encountered only 2 milliseconds of latency, and this corresponds to a very complicated policy which has 3 levels of nesting and thousands of transitions. And another dimension was our memory overhead. You just need to carry 6 bits of configuration header, and that corresponds to, again, a very big VPA with thousands of states. With that, I summarize this work, the policy language, and the non-invasive mechanism that we've been able to implement because of this insight of treating service trees as nested words. And if you're interested to understand more about the compilation sketch or our future work talking about data dependencies and extending this work to async setting, do check out the paper. Yeah. Thank you.
Thank you. We still have time for questions.
Sure, I'll ask one. Hi, Karuna. Can you say something about how you came across the nested word formalism?
Oh, yeah.
Because I had not heard of it before, and it's interesting that it turned out to be such a good match for the problem that you were trying to solve.
Yeah. That's a good question. I have a really good answer. I think there was someone who pointed out the using regular tree languages. I don't know, someone in the audience. Yeah, we ended up looking at that because it was obvious. However, it was soon that we realized when you had to work, so regular tree languages are accepted using tree automata. They're just like your AST parsing. When we had to extend it for our setting, the way our serialized traces work, we found that extending it just made us arrive at nested word or visibly pushed down automata. And another slightly different but a technical reason is that tree automata will take in your entire tree and then process whether it is accepted or not. But in our case, in the runtime monitoring setting, you have an incrementally building trace, which means you need an automata which which supports serializability, and this one was supporting it. So yeah.
Okay, let's thank Karuna again.